So staying on the same topic here, eclipsing white dwarfs. So for those who don't know me, I'm Jan Van Roestel. I'm a postdoc at the University of Amsterdam. I actually used to be at Caltech until spring this year, where I worked with the Zwicky Transients facility shown here. So my interests are basically using large-scale time domain surveys specifically to learn things about white dwarf binaries. And today I'd like to talk about specifically using eclipses in photometric surveys as CTF to study white dwarf binaries. So a very quick background on short periods compact white dwarfs. You basically make them by taking two main sequence stars. One of them evolves, they go through a common envelope, and you get out a white dwarf and a main sequence star. Of course, depending on the orbital separation and the mass of the components, you can have further evolution in different scenarios. For example, you can make CVs from stable brush lobe overflow, or have another common envelope and make double white dwarfs. So there's lots of different ways to make these, or different channels that all make different kinds of compact white dwarf binaries. And these binaries all have short orbital periods from days or weeks, but down to hours or even minutes. Right, so the second thing, eclipses. So why am I so interested in them? Basically, well, they're a very useful tool for two reasons. Detection method, and Keaton already talked about that a lot, but they're very useful because it's a very clear signature in the data. It's a well understood selection method of finding objects. You're also able to find dark objects like exoplanets moving in front of a brighter star. And we've got lots of photometric data to apply these searches for eclipses. Of course, there is a disadvantage. You can only find things with the right inclination. So in the best case scenario, where you basically the stars are close to each other, you still only find 8% of the objects because of inclination. This rapidly decreases as the orbital period increases. Of course, the second advantage is you can characterize these objects. For example, in most cases, not always, but it is easy to measure the orbital period. From the eclipse depth and duration, you can measure radii and temperature ratios. However, if you only got an eclipse light curve, you can't measure masses or a semi-major axis. So I just want to note that finding an eclipsing system is very nice, but you can't do everything with it. You do need to have some follow-up to fully characterize it. CTF was already introduced, so I'm just going to put this slide up here. Basically, it's a camera looking at the sky. It's observed 2 billion objects with light curves, about 800 epochs by now. Lots of data, lots of light curves to look at. And as Keaton already introduced, CTF has these alerts where you can find basically disappearing stars, and that's what I've also been doing. But I specifically focused on a periodic repeating disappearing events. So I basically took the ZTF data, the light curves and the alerts, and coupled that with the Box-Lee square method to find basically a box-shape recurring signal to pick out eclipsing white dwarfs. And of course, there's many other people who've already done a similar thing here. So before I go to the results, I briefly want to show you this diagram, which gives a really nice overview of all the different types of white dwarf binaries we know of and we expect to find. So on the y-axis is the accretion rate, on the x-axis the period, and down here are the two non-accreting types of systems, the double white dwarfs, which go all the way down to 10 minutes or even shorter, and the white dwarf main sequence stars. And for example, if you're interested in ZTF discoveries of double white dwarfs, look at Kevin's work. I think that was missing. Yes, Matthew already showed something about eclipsing AMCVN systems, so you can find one of my papers on that too from ZTF. But in this talk, I want to focus on the white dwarf main sequence systems, or white dwarf with non-degenerate components, and also some of the very low accretion rate cataclysmic variables. Right, so if you look for eclipsing white dwarfs in ZTF and you keep very careful track of them all, this is what I found by doing that. Let me just clean this up a little bit and remove some of the accreting systems. They're also very interesting, but dealing with this, the non-accreting sample alone is already a lot of work. So these are about 600 detached white dwarf main sequence, either M dwarf or brown dwarf, eclipsing binaries from ZTF with a good Gaia distance. There's about 200 more which don't have a good Gaia distance, so I removed them from the figure. The color here indicates the orbital period, so red is 70 minutes, the period minimum, up to 1 day, but it actually extends all the way to 6.6 days is the longest period system. Just to give you a sense of what these look like, so on the top left, you've got white dwarf systems, or white dwarf binary systems with a hot white dwarf, which is irradiating the companion, and you get this huge reflection effect. On the top right, you've got systems which are dominated by the main sequence star. You typically see ellipsoidal variability where, due to gravity, the main sequence star is deformed, and you relatively shallow eclipses. And here on the bottom left, you find white dwarf systems with very dark companions, so typically brown dwarfs, but also the giant exoplanets Keaton mentioned. And to the right here, you've got systems with both a cool white dwarf and a cool main sequence or brown dwarf, actually main sequence system down here. So I won't talk about all of these yet, but I just want to focus on the bottom left of the HI diagram, so the white dwarf with cold companions. And Keaton already introduced it, but so this is ZTF J038 plus 20. And the reason why it stood out is because if you look at the SED, you basically see no infrared excess, although you do see it disappear basically every 10 hours. So that's why I got very excited, and Keaton as well. We thought this might be a white dwarf with a giant planet orbiting it. And it, of course, giant planets can only occur far away at orbital periods of about 8 hours or longer, because they get disrupted if they get to shorter periods. So we were very excited. Unfortunately, if you get radio velocity measurements of this one, it turned out to be a very cold brown dwarf. As you can see, there are a few other candidates there, but nothing, unfortunately, is a transiting giant planet. Right. We did find some other things in here. So if you take ID spectra of objects down here, which are all eclipsing white dwarf systems with deep eclipses typically, you actually find systems which have a double peak emission line. And I was somewhat surprised, because if you look at the ZTF light curve, it's just a flat light curve. There's nothing going on. There's just an eclipse. But these are actually low accretion rate CVs. So CVs that have such a low accretion rate that there's no flickering, no outburst. And these are some of the missing population of CV period bouncers, where the CV has evolved to the period minimum and is now moving out again. And interestingly, the longest period system here is 125 minutes, so slightly over 2 hours, which is a bit of a surprise that these systems can exist at such long periods. So I mentioned, so these were just a few highlights. However, it would be nice to get, instead of getting observables, actually try to get binary parameters of this whole sample. So I thought, well, we do have all the light curves, which gives you radii, temperature ratios, and an SED, which also gives you additional information about the temperature, but also the absolute radius instead of the radius ratio. And we've got Gaia distances. So in principle, we should be able to determine all binary parameters for all these 600 systems. That's easier said than done. The data is very inhomogeneous, and making sure the data is clean and you're not accidentally matching to a different source has been quite a lot of work. But I actually think I have now managed to measure all the binary parameters for all these systems. So you can do, I'm still doing the quality assurance here, but some interesting things you can think of doing, basically looking at the white dwarf temperature versus log G here. You can find basically white dwarfs in binaries, white dwarfs in the ZZ SETI strip, which are in these eclipsing binaries. And of course, that would be very useful to find a pulsating white dwarf in a binary, because you can basically use both methods to measure the white dwarf's properties. A second thing which I'm trying to do is, which I'm showing here, is again period on the x-axis versus the Roche-Loeb fill factor of the secondary. So basically, how much the secondary star is filling its Roche-Loeb. So if all the stars on the top are basically cataclysmic variables, and this nicely shows that basically as you get to shorter periods, the secondary star is slowly filling its Roche-Loeb more, and at some point they reach the top and they will become a CV. Interesting prediction about from CV evolution is that they're supposed to detach that at about 3 to 2 hours, which is that red triangle there. And one of my master projects was about these so-called CV period gap objects. And that was actually my motivation of looking at this sample, is can we identify these CVs crossing the period gap by finding an axis in that region. Unfortunately, I don't see any significant statistical access. However, this does allow us to do a more targeted search and basically take those objects in that region and characterize them better with follow-up spectra. So let me end here with a summary, and thank you for your attention.
Thanks, Jan. Questions for Jan?
Thanks, Jan. That's amazing work. Really, really cool. Looking at your log G versus, I think it was, your ever log G is below 8, right? So it's not, you're not looking at your Ming mass is not the Ming white dwarf mass, it's probably a lower mass, but it also doesn't go very low. You don't find that many low mass white dwarfs. Do you know why is that? Is there any bias in your selection? Because I would expect them to be easier to find even maybe.
Yes. So I have to say, I finally got this to work last week, so I haven't looked in all the details yet. It's much more difficult than I thought it would be. So statistically, yeah, that's a good thing. I should still look at all the average statistics. There is one white dwarf which actually has a very long eclipse duration. It's also extremely hot, and the model suggests it's actually a 0.04 solar radius white dwarf, so that suggests it has to be low mass. Interestingly, it's also the longest period system, maybe not surprising because it's easier to detect if your white dwarf is large. So yeah, there are some interesting low mass systems in there for sure.
Yeah, I just wanted to comment on this. I mean, in the post-common envelope binary survey that we did, we didn't discover any extremely low mass white dwarfs because basically they do not survive the common envelope. So we stopped at 0.4, 0.35 was the minimum we got at that time. So you don't expect them in this sample in large numbers.
Yeah, I can say that they're definitely rare, and we found one which might be a low mass white dwarf. Yeah.
Jan, I'm not sure this is a question for you. Maybe you don't know the answer, but in the audience, someone may know. Is there any estimate what's the lowest mass transfer rate after which you will not have accretion disk? You will have bounce back system, but no emission from the accretion disk.
Well, I'll give the observational answer. We basically are finding them up to 125 minutes, so 2 hours, which is very long. So I'm saying you always see an accretion disk. However, there has been some discussion during the workshop that people think they do detach at some point. But well, I don't know how you explain this 2 hour, 5 minute system then, but I don't know, Anna or Matthias want to comment.
So this is really amazing. And I've got one question for you, sort of, what's the next step? So you've got the sample of the faint ones. One thing I was thinking about was higher up on the main sequence, there should also be some eclipsing systems, but the depths would get really shallow, right?
Yeah, yeah. So I definitely, this region is very incomplete. As you can see there, the R band eclipse is barely visible. The G band eclipse, well, you still see it in ZTF data. Yeah, that's an issue to find really the systems in the here. You probably want to look at some UV access search. Yeah, and at some point ZTF data won't be enough. Or you need to do something with tests or something.
Yeah, that's what I was going to ask. I was actually wondering if some exoplanets might actually be white dwarfs that were misidentified as exoplanets.
I'm just going to finish this sample first before moving on. This is way more work than I.
Yeah, really nice job.
For.
Hi, it's really interesting, the work you're doing. Actually, if you can come back to the CCCT thing you showed. That one. Yeah. Unfortunately, I cannot see the numbers, but actually, if the CCCT instability strip is quite not very well populated, below 0.4 solar masses or so, and actually, I don't know if that is a selection effect or there are actually no pulsating white dwarfs there. And also it's a great area because they could be helium or carbon oxygen core, depending on the evolutionary path. They should be binaries, but some of them won't. So it's a very a lot of possibilities to form those stars. And one way to figure out that is by using astroseismology. So and actually the instability strip will go a little cooler than you show, so you might have more objects there that are interesting.
Yeah, so it's not the highest resolution figure, but some of the error bars are this large. So I think this is more a way to focus our high-speed photometer follow-up resources, and well, probably pick out that slightly broader region than this, just to make sure we're not missing anything.
Yeah, usually the best way to do a selection is just put all the ones that we know are pulsating. That's what I do, the selection of the sample I want to observe. I'll just use the ones that I know are pulsating and see which ones are on top of those. But that's really interesting.
So the thing is, observationally, you can't do this because you've got an M dwarf there, so the colors are all messed up. So we really need to do the modeling to figure out what temperature the white dwarf is.
Okay, thank you.
Can I just add a very brief comment, which is that I also think you should push to higher temperatures because these are going to be accreting winds from the M dwarf. And Valerie Van Roestel had some nice work on driving and pulsating white dwarfs, motivated by CVs, but those can be driven at 15,000 degrees and 17,000 degrees. So, yeah, you may not want to restrict just to the typical instability strip. You might even get to go higher.
Well, you have to find them. You need high-speed follow-up, and there's 800 systems, so you need to make a choice somehow. But yeah, it's definitely worth considering.
Thanks. I wanted to ask about the period bouncers. So there's this whole literature about missing period bouncers.
Yeah.
And the selection effects are a little bit important, but I would guess for that population, they're more tractable to model because, you know, the white dwarfs are cool and it's mostly just geometry.
Yes.
So do you have an estimate of how many there are and how it compares to?
Oh, yeah. I didn't mention that. Yeah. So, I mean, I've done something very similar with the eclipsing AMCVMs here, but taking these 5 and trying to correct for all the ZTF selection effects, it's about 10 to 20% of the overall CV rate. Yeah, but it's N of 5, which is. Yeah.
So if you go back to your other diagram that you just had up there, yeah, that one. So could the ones, because you're not seeing a gap, but some of those could be magnetic CVs, right? Or would the eclipse look different for those so that it would be excluded from your sample?
there are definitely some magnetic systems in here. I actually removed them from the sample because you can't properly model the eclipse.
Oh, okay.
But they're definitely in here as well.
Okay, let's thank Jan again.
Thank you.